Hi, I'm Steve Sandler, the founder of AEi Systems, a company that specializes in modeling, analysis, and simulation. A large part of our focus is on analog and power electronics, though we support RF and instrumentation as well, primarily for the high reliability arena. In our business, we're frequently called on to assess and troubleshoot system-level issues, many of which are related to the power distribution network. The problems we tend to encounter are generally related to issues such as noise, PDN-type transients, clock problems, and EMI. The causes of the customer issues are generally covered in this very short list: stability, EMI, switching issues, distribution issues, and subpar performance. In a previous video, I discussed the value of impedance measurements in assessing the noise and stability performance of distributed power systems. In this presentation, I'll discuss techniques for measuring impedance. We have two basic options for measuring impedance in the frequency domain. We have the Frequency Response Analyzer, or FRA, and the Vector Network Analyzer, or VNA. While these two instruments seem similar, they're actually quite different. The FRA, which is also known as a Low Frequency Analyzer, or LFA, or gain phase meter, typically provides a low impedance oscillator output and two high impedance ports designed for the purpose of measuring gain and phase as channel 2 divided by channel 1. The VNA typically has two 50-ohm ports and can measure S parameters S11, S12, S21, and S22 as gain, impedance, reflection, or admittance. Generally speaking, a VNA offers more capability than an FRA, though traditionally most VNAs start at frequencies that are above the range of interest for power and analog circuits. But as we'll see, in this presentation, there are VNAs with frequency ranges that extend low enough to suit analog and power circuits. The VNA also has the capability to calibrate and de-embed the cables using short, open load calibrations, as well as using a through calibration and a propagation delay necessary for measuring small values of inductance. There are currently two analyzers on the market that can perform as both VNA and an FRA. One is the Omicron Lab Bode 100, and the other is the Agilent E5061B. Both of these analyzers extend low enough in frequency to support the measurement requirements of most typical analog and power applications. The Bode 100 offers a range of 1 Hz to 40 MHz, while the Agilent E5061B uses two separate instruments. Its FRA provides a range of 5 Hz to 30 MHz, while its VNA offers a range of 5 Hz to 3 GHz. In this video, I'll focus mainly on the use of VNAs to perform impedance measurements, specifically discussing the benefits of single-port measurements, how to perform them, and how to interpret them in the context of troubleshooting distributed power systems. Then in a follow-up to this video, I will extend the discussion to two-port measurements. But before we begin to discuss measuring impedance with VNAs, we need to understand the essential role of interconnects in making high-fidelity impedance measurements. One of the major shortcomings of high-fidelity measurement is the lack of high-fidelity interconnects between the device under test and the test equipment. Many of our customers believe they've made good measurements while they've actually measured the limitations of their test equipment. One example of a common measurement error is to use a 10 picofarad scope probe to measure the switching frequency via the pulse width modulator oscillator ramp. The 10 picofarad capacitance of the probe is enough to significantly alter the results. In order to overcome these types of issues, we've developed a complete line of link devices that provide a high-fidelity interface between the device under test and the analyzer. In some ways, these could be viewed as high-performance probes. There are many devices in the product line, each designed for a particular purpose. Originally, we designed these devices to fulfill our own troubleshooting needs, but since 2010, we've made these link devices available for purchase through Picotest. Among these link devices are several signal injectors that work with both of the analyzers we've discussed, as well as with FRAs and general test equipment from various vendors. The simplest of the VNA impedance measurements is the single-port reflection measurement. This measurement can only be made with a VNA and not an FRA. The single-port reflection measurement is capable of measuring impedance over a range of hundreds of milliohms to approximately 1,000 ohms. This measurement method is most useful for measuring the impedance of low-power circuits, such as low-power linear regulators, voltage references, and op amps. We also frequently use the single-port reflection measurement for measuring devices, such as semiconductor junctions, MOSFET gate resistance and capacitance, ESR, and typical inductors. The measurement can operate on devices that are either powered or not, so it's capable of measuring at 0 volts, though the range is limited to relatively high impedance levels. In this example test setup using the Bode 100, the reflection measurement can be connected directly from the VNA port to the device under test, so long as the device voltage is less than 5 volts and the device under test can tolerate the 50 ohm loading presented by the VNA. In other cases, we can AC couple the measurement using a blocking capacitor such as the J2130A DC bias injector, which can provide the blocking capacitance and also provide a bias resistor that can be used to bias capacitors, optocouplers, voltage references, and semiconductor junctions for measurement. After making the physical test setup shown here, we configure the Bode 100 VNA to measure impedance using the on-screen menus. The single-port measurement is fundamental to our modeling effort in addition to being able to troubleshoot through in-system measurements. One-port measurement techniques can be used to measure the impedance of many different active and passive devices, and even to extract the junction spice parameters for active devices. Let's look at 2 example one-port measurements taken with the Bode 100. This slide shows an example of the single-port reflection measurement, which is applied to measure the gate resistance of a MOSFET. The low-frequency noise observed in this measurement is due to the fact that the gate bulk resistance is very small compared to the reactance of the gate capacitance at low frequency. This is the reason most MOSFET gate resistances are measured at 1 MHz. If you look closely at the photo of the test setup, you'll notice that the J2130A was not installed. In this case, the DC blocking provided by the J2130A was not required, as the CISS, or input capacitance of the MOSFET, provides that function. Here we show the results of a single-port measurement of the impedance and phase of a wet tantalum capacitor. The extracted data has been used to generate a spice model, which is also shown in this image. Again, in this case, the measurement did not require use of the J2130A since the device under test is at 0 volts and no blocking capacitor is necessary. This is yet another example of the single-port impedance measurement. This time the device being measured is Analog Devices' REF03 voltage reference. We generally measure signals in pairs so that we can make comparisons between the 2 measurements. In this case, the faint red trace is the impedance of the reference without the load capacitor, and the darker red trace is the impedance with the 0.1 microfarad load capacitor installed. The use of this capacitor is something that Analog Devices strongly recommends in their datasheet. As we observe the measurement across the frequency range, we can see the DC resistance at low frequency and then the effective inductance that results from negative feedback. Next, we can see the peaking at 100 kHz caused by the low phase margin, and finally we can see the capacitance. The stability margin can be calculated from the impedance peak and associated Q. Here we show the time domain image so that you can see that the effective inductance is dependent on the operating current, and also that the vendor's strong recommendation to use a 0.1 microfarad capacitor with the reference is actually a bad idea. This measurement can easily be made in system. At AEi Systems, we make this measurement very frequently. We use this most often for in-system measurement of op-amps, voltage references, and low-power voltage regulators. Hopefully, this introduction to measuring impedance using VNAs has left you with a greater appreciation for the versatility of these instruments in testing power devices and power systems. This video focused on using VNAs to make single-port measurements. In the next installment of the Troubleshooting Distributed Power Systems video series, I'll describe how to use vector network analyzers to perform and interpret 2-port impedance measurements. For those interested in delving deeper into the topics discussed in this presentation, see the references listed here. And if you have any questions about the information presented here, please email me at steve@picotest.com. Thank you.